In this video series, I'm going to take you through solubility rules and net ionic equations, and then the primary focus will be the latter parts of the series where I talk about solubility product constants, also known as KSP values. So to start off with, the next thing that we have here, this is a list that you would see in a lot of textbooks, and this is a list of water solubility rules, and then down at the bottom we have acid solubility rules. I'm not going to focus on the acid solubility rules at this point in time. I'll get into those more later on when I talk about KSP and Le Chatelier's principle and equilibrium. But just to summarize these rules real quick, rule number 1 on here says group 1 metal ions and ammonium salts are all soluble. So that means anything that we have, any salt that has sodium, whether it's sodium sulfate or sodium chloride, potassium nitrate, any of those, group 1, or ammonium, also would include ammonium sulfate, for instance, ammonium carbonate. Anything with group 1 or ammonium is going to be aqueous. Rule number 2, I call that the nitrate rule. It also includes the chlorates and the acetates, and all nitrates, chlorates, and acetates are also aqueous. The ones that are slightly, I'm not going to go into too much detail at this point as to what's slightly soluble and what's not. Rule number 3 is the chloride rule, also known as chloride, bromide, and iodide rule, and that's all chlorides except lead, mercury, and silver. Now lead is soluble, but it's only soluble in really hot water, so we're going to call that all but lead, mercury, and silver for rule number 3. Rule number 4 is the sulfate rule. All sulfates are soluble, all sulfates are aqueous except, in this case, lead, mercury 1, barium, and calcium. I'm over on the insoluble side there, giving you the exceptions. And the good news is if you learn these first 4 rules, it actually encompasses the rest of the rules that we have here as well. And a lot of books go into way too much detail, so I'm going to simplify this for you as much as possible. Rule 1, group 1 or ammonium, it's going to be aqueous. Rule 2, if it's a nitrate, it's aqueous. Rule 3, halide rule, chloride, bromides, and iodides specifically, all but lead, mercury, and silver. Sulfate rule, all but lead, mercury, barium, and calcium. Alright, so the next question becomes, what exactly is a net ionic equation? Well, some books call this an equation where we have omitted any unchanged ions, and that's what a net ionic equation is. We take out anything that's in ion form, meaning anything that's aqueous in solution, anything that's soluble in solution, and as long as we break it into ion form, and as long as it's unchanged from one side to the other, we call those spectator ions, then we eliminate those, and what we're left with is called a net ionic equation. So the first net ionic equation I might give you might be a sentence that says solid magnesium is burned, and I might say, you know, write that reaction, balance that equation, and ultimately give me the net ionic equation for that. So solid magnesium is burned. Now we have to know that is burned means it reacts with O2, oxygen, gas. And when I look at this, again, I use the word is burned. You might want to call that a combustion reaction, but really it's easier probably to see that as a synthesis reaction where we get MgO. And again, the reason why it's MgO is magnesium is in group 2A, so plus 2. Oxygen's a minus 2, so it's MgO. To balance that equation, 2, 1. And 2. So there's my balanced equation for this. And then the next thing is to go through and assign any subscript for anything that's aqueous. Well, if we have just a solid and a gas, there's not any water present, there's not any other solutions present, so really the solubility rule doesn't apply over here because there's not any water to even worry about. As a matter of fact, this, when we simply just burn that, is actually a solid product. Now, why do I do that? Because to do the net ionic equation, I have to properly assign those subscripts. Now I'm going to break apart anything that's aqueous. There's nothing to break apart. So once I've broken apart what's aqueous, I'm going to cancel out the spectator ions, and what I'm left with is the net ionic equation. So in this case, the balanced chemical equation is, in fact, the net ionic equation. It's also a good place to go through some alternate classifications for this. I said yes, we would probably call this a synthesis reaction. Because I said is burned, arguably you could call this a combustion reaction as well. There's also one other thing that we could call this. If we take a look, magnesium went from a 0 charge to magnesium over here, 2 charge on that side. So the magnesium was oxidized. Oxygen, on the other hand, no charge in O2 gas to a -2. So it was reduced. So this is a redox reaction as well. So there's really 3 classifications. Now in terms of predicting products, that one's probably the best. In terms of what we would see, maybe combustion is a little bit better. In terms of what's going on with electrons in this, then the word redox tells us about something that is gaining and something that is losing electrons as we go through this net ionic equation. The next one here that I want to do is solid sodium oxide is added to water. Now water is a liquid, so when we put a metal oxide in water, we produce a metal hydroxide. So we get sodium hydroxide. Na is a +1, OH is a -1, so it's NaOH. To balance that equation, I get a 2 there, so I get 1 to 1 to 2. There's my balanced chemical equation. Now I'm ready to go through and do the net ionic. Now this one's a little bit different. Because we have water present, then we have to ask ourselves, what is sodium hydroxide? Well, there's 2 ways we can do that. It is a group 1 salt. It's also a strong base. And anytime we have a strong acid or a strong base, then those are also going to be aqueous. And again, this applies because we have water present. So now I'm ready to break apart anything that's aqueous. So that only involves breaking apart what we have on the product side. So really what I did to put this together, I'm now going to undo and make 2 Na plus aqueous ions plus 2 OH minus aqueous ions. So there are the products. The reactants remain unchanged because this one was a solid. This one was a liquid, so there's nothing there to break apart. And in terms of canceling anything from one side to the other, there's not any Na plus or OH minus on the reactant side, so I just leave it with this on the reactant side and this on the product side, and there is my net ionic equation for that one. The next one that I want to do is solid calcium carbonate is heated. So CaCO3 solid is heated. Type of reaction that we have here when there's only one reactant is going to be decomposition. And the decomposition of a carbonate gives me, in this case, calcium with oxygen, calcium oxide, +2 minus 2, and CO2. Now we know that carbon dioxide is a gas. And in this case, we got this solid here, and calcium oxide is also a solid. Again, I'm not going to any solubility rules because all I had was a solid. There's not any water present. There's not any solutions present. So there's nothing here in terms of solubility rules to apply. I'll balance that equation. 1, 1, and 1. Nothing aqueous to break apart. So the reaction for this decomposition reaction that we have is the same as the net ionic equation as well. Some of these early net ionics are a little bit boring. I'll get into the ones where it's a little more applicable here in just a moment. The next one, propane, C3H8 gas, is burned. Again, is burned plus O2. Now we're combusting a hydrocarbon, so we're going to form CO2 plus H2O. So here we've got, this is a gas, and where we're combusting this is going to be a gas, and initially this is going to be gaseous water vapor, and then of course if we're at room temperature, once it cools back then it would be a liquid. But either way, there's nothing there to break apart. There's no solubility rules, so the equation will be the net ionic equation. This, by the way, is a combustion reaction. And to balance this equation, 3 carbon, put a 3 in front of the CO2, 8 hydrogen, 4 in front of the H2Os, and I've got 3 times 2, which is 6 oxygen, plus 4 times 1 is 4 more. 6 plus 4 is 10, so I need a 5 there. So it's 1, 5, 3, 4, and that balanced equation is, once again, the same as my net ionic equation. Now notice, comparing that one to the previous one, here we use the words propane is burned plus O2. In the previous one, we said calcium carbonate is heated. There is a difference in heated and burned. Alright, so the next one, and this is where we'll get a little more detail as far as what an actual net ionic equation is going to look like. For this one, we've got solid aluminum is added to a solution of copper 2 nitrate. So again, from those words, hopefully you know nomenclature well enough, solution of copper 2 nitrate. You got to be able to do the nomenclature at least to get started, and if you look at that, you would probably guess that that looks like a single displacement reaction where aluminum goes with the nitrate, AlNO3 because aluminum is a +3 charge, and copper ends up alone. Now, I do a whole series on single displacement redox reactions and then ultimately some electrochemistry where I go into a lot more detail on this type of reaction. For here, I'm just focusing mainly on net ionics, and I said the word solution of copper 2 nitrate, so I gave you that. I didn't tell you that it makes a solution, but we learned from solubility rules that all nitrates are aqueous. And then lastly, this copper that we have formed is going to be solid copper. So now I'm ready to go through and balance this equation. And one aluminum, one copper, but I ran into a small problem. 3 nitrates on the right side, on the product side, 2 on the reactant side, so I need a least common multiple. 3 there gives me 6 total nitrates. 2 there gives me 6 total nitrates, and now I got to go back and fix the aluminums and the coppers as well. So there's my balanced single displacement reaction. We also know from that other lecture that this is called a redox reaction. We'll see that more so here in just a moment as we go on through this net ionic equation. So we're going to break apart anything that's aqueous. So again, by balancing this in the beginning, it makes the net ionic easier. I do show you how to balance net ionic equations without the spectator ions in that other video. So if you have questions on that, check out the video on redox reactions and electrochemistry. So because I've already balanced it, I'm just going to carry the coefficients through here. 2 aluminum solid plus 3 copper plus aqueous ion. So all that work that we do when I say solution of copper 2 nitrate, and you have to know enough nomenclature to write that formula, essentially when we get to a net ionic equation, we're taking this back apart. So 3 coppers, now 3 times 2 nitrates is going to be 6 NO3 minus, again 3 times 2 in parentheses, and now I'm ready on the product side. I got 2 aluminum nitrates, but we said those are also aqueous, so that's going to be 2 aluminum plus 3 aqueous ions, and again 3 times 2, 6 nitrate aqueous ions, and then lastly 3 solid coppers. Alright, so now I'm ready to break apart any spectator ions or anything that's unchanged. Well, I've got 2 aluminum and 2 aluminum, but they're not the same. This aluminum is 0 charge aluminum, and here it's oxidized into aluminum with a +3. 3 copper plus 2s and 3 copper solids, that's being reduced. It's not the exact same thing. However, 6 nitrates and 6 nitrates, those are unchanged. So I'm going to take those out in this net ionic equation. We're going to leave those out, and we're going to rewrite this equation as 2 Al solids plus 3 copper plus 2 aqueous ions, forming 2 Al plus aqueous ions and 3 Cu solids. So here is my net ionic equation, and it gives me a picture of copper being reduced and the aluminum being oxidized when I take a look at that net ionic. Now again, if I took the coefficients out, I go through how to balance those by half reactions in that other video, so feel free to check that out.